Hello everyone again to my YouTube channel. Uh, Today in this session, I will discuss with you one of famous algorithms that we have in machine learning. This algorithm can help us to solving some kind of problems, uh, classification and regression problems. I mean, the first type machine learning. In this session, I will explain to you what is the support vector machine and what is the math behind this algorithm. Well, it's starting. So, support vector machine, as I told you before, is an algorithm to solving some problems in classification in the regression problem. Okay, uh, so we can use this algorithm to classify or to predict some values based on the feature provided in our dataset. Well, this support vector, when we use it to solving the classification problem at this time, this algorithm called SVC, support vector classifier. Okay, and if we use this algorithm to solving regression problem at this time, this algorithm called support vector regression. Okay, so I hope that's point clear for you. Okay. So let's start in with some basics. Well, uh, as we know in linear algebra, to draw some line, we need equation. Okay. Well, as we see with me in this figure, we have this x-axis and y-axis, and we have this line here. Okay. Well, to draw this line, we need an equation to draw it. Okay. So as we see with me in this left side, we have some denote of equations. The famous denote to draw a line is writing like that. So we have y equal to m times x plus c, or we have y equal to beta 0 plus beta 1 times x, or a times x plus b times y plus c equal to 0. So all these three equation is the same. Okay. Well, if we look in this third one, a times x plus b times y plus c equal to 0. If we want to find the value of this y or to extract this y, then pass from here to here, and it's easy to find y. What we can do in this case, we need just divide all these equations by b, and that's what we do here. We looking with we dividing a divided by e and also b divided by e and c divided by e. Okay, and to find this formula, we need just to pass this coefficient, okay, to other side. Okay, a times x divided by e. If we change place for this equation or for this coefficient to other side, sign of this coefficient should be changing. Okay, these things is basics in mathematics. Okay, we are taking this term, or we take this term, all this term from here to another side, and we are changing the sign of this. So the same things for this c divided by v. We put it on the other side, and the sign should be changed. And finally, we found our formula: y equal to minus e divided by v times x minus c divided by v. And this term called intercept, and for this called coefficient or slope of this line. Okay, so in this case should be negative. Okay, here if we try to draw a line based on this equation that we have here, this line should be like this, should be negative because we have this coefficient is negative. Okay, if we take in of course some positive points. Okay, well, the whole idea of the equation, we need to know the coefficient and the intercept. I hope that's clear for you. So if we go in the bottom, so we see with the its axis x1 and x2, and we have this equation is the same. Well, we have this a times x1 plus b times x2 plus c equal to 0, and we have also w1 x1 plus w2 x2 plus b equal to 0. So both of these equations is the same, but in our explanation we taking this notation because this denoted is writing in the search paper, sorry, the scientific papers. We are kind of find this kind of notation here. It is easy, and this equation represent the same things. So we have here w transpose x plus b equal to 0. Okay, this notation is transpose because in linear algebra we have some vectors and some matrices at this time. If we multiply a single value to a matrix or to matrix or vector to matrix, we need to transpose this vector and matrix to make this operation. Okay, so this equation is the same. W transpose x plus b equal to 0 is the same equation. And we have a special case if the line is passed from the origin of this axis at this time, w transpose times x equal to 0. Okay, because this line is passed from the origin. Okay, this time y equal to a coefficient times x. Okay, cos and b in this case is 0. Okay, so I hope my writing clear for you. Okay, in this case b is equal to 0. Okay, well, let's continue. So as I told you before, we work in the space and place. I mean, we have a lot of features, a lot of values, constitute matrices and vectors. For the reason we need this concept of transpose. So if we're taking this matrix multiplication, we have w1 and w2 as the value, and we have also x1 and x2. Okay. So this notation of WTX is called W transpose X. W transpose X, because this W is a vector, and also is this X is a vector or another vector. Okay, so we have raw features, law of volumes. The equation of the line passing through origin is W transpose X equal to 0 as I stated before, because it is passed in the origin of axis. So if we continue, see within this figure, here we have this plane. Okay, this is a plane called V plane, and we have this weight. Okay, we have W here is magnitude. I want to explain it there. Well, we see with me we have some points here with this blue color. Okay, we have point here, we have point here and here, and we have, if we consider this point P1 with two coordinates x1 and x2, and we see this point is projected in this plane. Okay, we have the projection of this P1 in this plane. Same thing is for P2. Okay, we have the coordinate and we try to project this P2 in this plane. We have also some other points here. Well, the whole idea here, we try to see this angle that we have here. Okay, we have this W here, it's called unit or direction. And we will see that after. And we try to see all the values of the points that we have here in this angle. All the points that we have here in this part of this plane should be less than 90 degrees. Okay, if you take any point here, you see all these things is less than 90 degrees because we have in this whole space. And for other side or the other angles, so each point here is more than 90 degrees. Okay, because here we have the 90 degrees here. And if we take in this point, for example, we try to project it here, we get more than 90 degrees. And we will see that why that is very important. So we have to find the distance of point from the plane. So we have a plane here, and we need to find the distance for each point that we have here in our plane. Okay, and line P equal to line is in 2D, 2 dimension, and we have plane in 3 dimension. So the whole idea of that is to find a distance. Okay, distance for each point. Distance of point plane. So we have the distance of V is equal to W transpose P divided by the magnitude. Okay, equal to magnitude of W times W of P, the point, times cos of theta. It cos of theta. Well, where the transpose of P1, W transpose P1, and W is a vector. Okay, the notation just denotes. We try to explain it more. We have W transpose P1 is W transpose P1, and we have W is transpose vector, and we have the magnitude of W, magnitude of W. Okay. Well, if we take an example here, okay. So we have this triangle, we have this D, this distance. Okay. Try to calculate how to find the value of this distance. We have some measures for this. We have 3 by 4. And if we try to calculate this D based on the example that we have here, D equal to the root of the 3 squared plus 4 squared equal to the root of 25, and D is equal to 5. So in this case, T is equal to 5 based on this. So it's a Korean theorem in mathematics. Well, so where the vector of the height equal to D divided the magnitude. And if we return to this example, we have this coordinate point, we have 3 divided by 5. 5 here is considered by the magnitude as we see in, okay? 3 divided by 5 and 4 divided by 5. 4 to G equal to the root of 3 divided by 5 squared plus 4 divided by 5 squared equal to the root of 25 divided by 25 equal to 1. So we, after replacing all the values that we have here based on this formula, we get 1 in the end as a result. So unit vector. So unit vector is a way to get the focus on direction mode and the magnitude. Well, this value just give us an idea about the direction of the plane or the point that we have in plane. You can see that uh, in more deeply in this with other examples, it will be more clear. Okay, the value of this is just for the direction of the magnitude. Well, so the whole idea, as I told you before, is that so upward vector. So we are calculating the distance based on this. So the equal to magnitude times p1 or magnitude of p1 dot cos of theta. So as we see with me here, this is a plane, okay, and this is the point. You can find it other points here, here, or here, okay. But in this example, we're taking this point of p1 with coordinate x1 aka 1 1. So with this plane, and we have this angle with 90 degree, considering this direction that we have here. Well, any point that we take in here, okay, any point that we get here should be less than 90 degrees, okay, and this point is considered like positive point. So points above the plane, so we have plane here, and we have this point is above the plane. So this point above plane is positive point, it's considered positive point. And in the other side we have this point in below of plane. Okay, we have other points here and here and here. All this point that we have here is below this point is negative point. It's considered like negative point, and also the degree of all these points is more than 90 degrees. Okay, so the cos theta should will be positive. Okay, any point that we take in here, if we try to after projection of this point here, for example, we calculating the theta, the cost of theta, and to calculating the cost of theta, we take in this measure here, this measure, okay, divided by this, the projection of cost. Okay, this divided by this will give us the theta or the cost of theta. Okay, well, any point found above the plane, then the theta must be less than 90 degrees. As I told you before, any point, considered, any point considered here, if it's below or above the plane, sorry, if it's above the plane, sorry, the theta should be positive. Any point here and below this plane, the theta should be, or the cos of theta should be negative, or considered like negative point. So we have this downward vector also. If we change in this w here and we change the direction of this point at this time, this point that we have in above this plane goes here. Okay, this point that we have here in top or in above the plane is considered negative because we consider it in this case the direction of this w is weighted. Okay, and any point we have here in the uh, bottom or in the below this plane is considered positive. Okay, so here as should be there because if we consider this angle here, any point we have here is less than 90 degrees, but any point we have here is considered more than 90 degrees. Okay, so the projection of each point that we have. So if we take in the example of P1 here, put in here, and here give us the ability to calculating this distance here. This time we're gonna fall more than 90 degree is negative point. Negative. And here is should be positive. Why? Because if we look in the direction of the one, sorry, of the ways, and the point that we have the direction, we're gonna calculate in the distance should be uh, or positive or positive. Well, cos will be positive and cos will be negative because here we have theta is more than 90 degrees and theta is less than 90 degrees. You have to criteria to consider it here in this case. Well, I will go to geometric intuition behind support vector machine. That is very important. So the idea we we have three lines here. So the first one or in the middle one here is the biscuit line. And when we're talking about biscuit line, I mean the best line that we can have here based on all the distance of this point, the green point and the green point and the blue point. Okay, and we have sometimes other called marginal plane. We have both sides. Because here it's a if we consider this example like a binary classification at this time, we need to draw to marginal plane. We have this line here. Okay, we have this straight line here, and we have marginal plane. Okay, and the the substance of this idea is to maximize this distance here. Okay, and this equidistance should be the same between the marginal and the line in both sides, in below and above this bit line. Okay, idea is to maximize this distance here. We need to separate the classes. We have in the top and in the bottom. We need to have this line or this point should be maximum distance to make it more clear. So in this case, just in preliminary, we need to separate these classes linearly. Okay, but we have other times we have a distribution or so this point is not cannot apply this approach of linearity to separate it. We need some other things to make that possible. Okay, so the whole idea here is to maximize the distance between 2 points. Okay, we need to maximize this. So we can have more than one support vector. We can draw another one here on the first one here. Sorry. So will be many possible hyperplane that separate different classes. As I told you before, we can draw more than one hyperplane. So we have learned in linear regression. So linear regression is another algorithm. I talked about that before on my YouTube channel, linear regression. Things are going also that the probability, because this is based on probability, of course. So the probability of the point belonging in a class given at very close, the hyperplane will be close to 0.5. Because here is called hyperparameter. All these points here should be close to 0.5 to classify. So we want to hyperplane that separate positive points and negative points as far as way possible. As I told you before, we need so I have not see me. Sorry, here we need to separate. We have positive point and negative point. We need to maximize this distance to make it more maximized, to make this separation more clear. Okay, because we need to finalize our model. That's why we need to maximize this distance. So the key idea of SQL virtual machine is to make this separation more clear and maximize this, the distance between the marginal points. Okay. Well, so if we take we through this figure, so we have hard marginal and soft marginal. So here the difference between both. So if we take in this marginal point, we have this point here is perfectly separated. I mean, we don't have any point inside or is more close to this fit line or this fit line, sorry. Okay, everything is separated perfectly. That's hard motion. I mean, you don't have any errors here. You don't have any other points close to this green one or any red one close to this blue one. So, but if we see this submarginal, we have some errors. So we have these classes, the red classes here, and we have the blue one. We have this point in the same cluster of this class, but it's more near to this red one. And we have also some other red points is more clear or more close to this cluster of blue one. That's soft marginal. So the marginal plane is line past to the nearest point. The marginal point is the marginal point. Okay. The marginal point is the marginal point. The marginal point also is one. So the whole idea here is to this marginal point should be passed should from or near point. Because we try to find the near point here. At this time we draw this line past near to this point. So here and here. So we taking this marginal, we have some points here, and this is the marginal pass to get this point. For the same thing here, we try to pass this marginal point in a near point. So we have hard marginal. In hard marginal, we will not find any error, and we will be able to clearly separate all the points by using the marginal point. That means we have zero error. So we see here in the hard marginal we have zero error because all the points is separated. So, but in the world, there will be many overlapping, many errors. So marginal plane will be called soft margin. So soft margin here we have overlapping. I mean, we have some points. So we have some points for this class or for this cluster. We have here, and we have some points for this cluster is here. That's what's called overlapping. Okay. We have errors. So this all these points here is errors, and all these points also is considered error. Okay. Well, so marginal plane should be equidistant from the specific line. I mean, if we look in this figure, we need to have the same space here from here, and also from here from here. We need this equidistant should be 4. So if we see the mathematical intuition, so if you're looking with me, this line we have here, we have this direction or this weight for direction, of course. So we have these points, positive points, and we have these negative points. Here, the equation of the line is W transpose X plus B equal to 0. This is the equation for this line. And if we go below, so we have this specific line, and we have the marginal here, the marginal here. So as I told you before, for this specific line, we have this equation of W transpose plus B is equal to 0. Okay, you see with me the equation for this specific line. And for the positive one, because we have this direction for this way, so if we have all these points as positive, well, W transpose x1 plus b equal to plus 1. I mean, this equation, or this is the equation for this margin point. This margin point, we have this equation for it. And for negative points, we have W transpose x2 plus b equal to minus 1. Well, how we can find this equidistance? So before, the idea is to maximize this distance right here. We need to maximize this distance. And to do that, we need just to partake in this first equation for this marginal point. We have W transpose x1 plus b equal to plus 1, and we have W transpose x2 plus b equal to minus 1. We need to extract one from another one. Well, this one minus this one, we get W transpose x1 minus x2, because b with b should be crossed, should be cancelled, because we have positive here and we have negative here after this sign of minus for all these things. Okay, all these things should be negative, and b should be b. All these things should be positive, and this b should be negative, and b minus b should be 0. And we have here 1 minus 1 is 2. We have transpose for W transpose x1 minus x2 is equal to. After that, we need to divide all these things with the magnitude of W, the magnitude of Y to W, magnitude of W. Well, what we found here is W transpose x1 minus x2 divided to the magnitude of W is equal to, sorry, so this is equal to 2 divided by the magnitude. Okay, magnitude of W, magnitude of W. Well, the distance, the distance equal to W transpose x1 minus x2 divided by W equal to 2 divided by W. Okay, this is the distance. And so after that, we need a cost function, because each algorithm is work with something called cost function, because we need to find the best value, and we can do that just with cost function. Well, here we have maximized value of 2 divided by magnitude. So the cost function, we need to maximize that. So by changing this value of W and B, we need to maximize that by changing the value of W and B. Well, here of 2 divided by the magnitude is the distance between marginal point. This distance, so the distance here, the distance, okay, so between this the distance between this marginal point should be maximum. Well, so we have this constant, so W, okay, WE or YE, sorry, YE is equal to 1 if we have W transpose of X plus B greater or equal to 1. So in this, so here, this is the input, and here the output. Okay, 1 if W transpose X plus B is equal or greater or equal to 1. But W transpose X plus B is equal to minus 1. In this case, is minus 1. Okay. The output of YE should be 1 minus 1. That's the difference of the equation that we have here. Is less or equal to, is less greater or equal to 1, or is less or equal to minus 1. Okay, but this condition, this constraint should be this. Why? Because W or YE, if y is equal to -1, and this also is less than this is equal to -1. What's happened? All these result or this output of this equation should be negative. Okay, and -1 -1 plus 1, and 1 is really equal to 1 is right. And if this positive or if this y is positive, y is 1, and this thing is positive also, 1 times 1 is greater or equal to 1 also is right. I mean, this condition should be positive, always should be positive in any case. Okay, I hope that's clear for you. Well, if we continue, so maximize to divide this magnitude by changing w and v. The v minimizing magnitude divided by 2, because in loss function we try just minimizing the value in multiplication. We know that all maximum multiplication we need to minimizing the values, we need to decrease the values. For this reason we need to minimizing the magnitude divided by 2 by changing w and v. I hope that's so clear for you. It's easy. Well, so loss function focus on minimization. If you look before, we need to decrease the values. Okay. Cost function. Well, see the cost function minimizing minus divided by 2 by changing w and v help the parameter. Well, minimizing w or minimizing the magnitude divided by 2 plus c summation of all the eta starting from 1 to w. Here loss soft margin because we have error material before and we reward data. Also we have the errors. So for this reason we need to concentrate this and see. So this is the hyperparameters in the algorithm. So we'll see what is CE, how many points we have, ignore for this misclassification. Because in this case of classification we have some errors. The CE can be any number, can be 1, can be 2, can be 3, can be 30. Here the meaning of this constant or the meaning of this parameter is how many points you can ignore for this misclassification. The hyperparameter material. And for this eta, so for eta, okay, this is the eta summation of the distance from incorrect data point. So if we turn to this place, yeah, eta what is so directional. So here in this line, sorry, show you the data within the meaning of eta. So this is the distance. We need to because here is the error. We need to calculate the distance here from here, from here. We need to calculate the distance of error here. So we need this distance, and also this distance. So we need to calculate these values of distance. That's what's called eta. For linear world, we're facing this kind of soft margin, not hard margin. Well, if we continue, so we have C and we have the eta summation of the error values. So here for Victor classify for C4 Victor regression, we have the same things. We have this discrete line. This is the equation of this line. Transpose W transpose times X plus B. And we have here transpose X plus B plus epsilon. We have W transpose X plus B minus epsilon. Epsilon is marginal error. So we have some errors here. So in this case of regression, I mean we have continuous value. We need to predict continuous value based on the historical or provided data. Okay, this is the equation. We have the same things, just we adding this epsilon here. Okay. Well, the cost function is the minimizing. Yeah, we minimizing this magnitude divided by 2 in classifier and eradication, and have this things is changed. Okay. Uh, so mean absolute error of this constraint, this absurd of ye minus we times xe is equal to epsilon minus or plus eta to epsilon plus eta, and epsilon is the margin of error in this equation. Epsilon is the margin of error beside original plane, and we have this eta error above the margin. Okay, we need to see how much of error we have above the margin. Yeah, so it's funny here because the parameter. So this is the eta. We need to see prediction of all these points are to see how much of error we have here. Here like eta, and inside of between this hyper between of this marginal plane, we need to see how much of error we have on this thing called epsilon. See the whole difference between predicted support vector classifier and support vector regression. We have epsilon and eta. Okay, so this is keeping adjusting. So eta to get the best margin. So we can see in corresponding in okay, this is the hyperparameter. We have epsilon, we have eta above the plane or above the margin. We see the how much of error, and inside between this margin with this bit line, we see how much of error we have. And that's clear for you all. Okay, if we give an example of the price, we try to predict the price of a house based on the size. So we can see that. So we have these points here. We have this equation transpose x plus b plus epsilon plus plus epsilon, and we have w transpose x plus b, and we have transpose y x plus b minus epsilon. And we see the much. So this is the predicted value here. Okay, there's predicted value. We need to apply the error based on this hyperparameter. So in regression, completing correct value because it will be continuous value. So it's a continuous value. Okay, this is predicted value. So to minimizing this error, we need to finding graph the epsilon and eta. Okay, two hyperparameters that we have in the case of regression. So I have two interesting questions. Outliers. SVM or support vector machine is impacted by outlier. In most of the case, of course, we have outlier. We have some values is out a range of data, and SVM is impacted by outlier. Plus standardization need in CPM. Yes, we need to perform normalization and standardization. Why we need normalization and standardization? Because if I give you some examples of try to predicting some values based on some feature one, feature two, feature three. So the units that we have in these features is different. Okay. Maybe we can have some prices with dollars, which number, and we have size of house is 8 meters. And we have some surface of the garden of these houses with also meters. I mean, or in the center or something like that. I mean, the whole idea or the big idea of standardization is we try to minimizing whole values. Okay, because in some features we can find some values high, and another feature is low. Okay, this interval is big. What is we need to minimize it? This is the idea for the normalization and standardization. So if we're looking for this special case, it's not special case, but you know, kind of facing that. Uh, so if we look at this shape or this, if we look on this data, the pattern of the data, how it is, not linearly separated. If we call, we try to use this linear separated, I mean, try to go from the straight line and line up, it's not possible to separate this data. That's what's called supervector machine kernel. The data is not linear. What do we know? We need to have what the path from 2D to the machine to 3D. We need to change the point, or we are adding other dimensions to make the data more clear. Okay, after that we apply for vector machine, that will be clear for us. High dimension more than low dimension. Okay, so simple vector here. So kernel is the C simple vector classifier. We have the speed line, we have linear separate the data, but here it's not linear separate because the shape or this pattern of data is different from that. We have circle here, we have two separate clusters. Okay, and when we are creating this type basic line and marginal line, we are actually solving the linear separated data. So we look in the data is linear separated. At this time, we can use just simple vector machine like this case. But in data not linearly separated, we will not able to create a basic line and not able to create a marginal line, even though created the accuracy will be very low. Because if we apply simple vector machine in this kind of data at this time, accuracy of this algorithm should be there is no need to do something. You need to make some transformation to make this work. So for this type of problem, we have some more supervisory kernels. So what does supervisory kernels or what does supervisory machine kernels is to apply some transformation. We need to make some transformation technique, some mathematical formula on data set. This transformation implies the dimension of data. As I told you before, if we have 2D, we need to see our data in 2D, 2 dimension. Supervisory machine kernels transformation implies the dimension of data. We need to make it in other dimension. Linear separate line will give the errors because we have the data here cannot draw somewhere specific line. It's not linear separated this case. So what we can do is to write in our equation y equal to x squared. Transform data from 1D to we have data here in this 1D, one dimension, and we make it in 2 dimensions. We make it now 2 dimensions by using this transformation. Y equal to h2. Now we are able to make this. And we can Simply, we are making this transformation. So, as you see with me, we are making this transformation. Y equal to x squared. We have the ability now to form this basic line. Let's separate these two classes that we have. Okay. So, we keep an examples of this square. If we think the values should be positive. Okay. 1 3 square is 9 and uh, 9 and so on. What is advantage doing this transformation? What is the advantage? So after the transformation, we can apply minimum severe or serious. Okay. After this transformation, we can use CR or serious. We convert them from the 1 to B and divide all the form into simple one, which called the linear series. Okay. Will be two classifiers. So the type of the kernels that we have polynomial kernel, we have KBF kernel and sigmoid kernel. Okay. Now polynomial, we take an example of polynomial kernel. So we have it. In the shape of the data in here, not linearly separated. So it's not draw the line and minus and see how this can happen. So we will need to make some transformation from 2D to 3D. To do that, so here, looking in the top view, we have this value in the top and the green one in the bottom. At this time, we have the ability, or we can using this simple vector machine, and we draw the specific line and the margins. Well, so the formula polynomial kernel is fraction of x1, x2 equal to transpose x1, x2 plus 1 d, and d is image. So if we are converting 2D or 2D from 2D to 3D into value of d is equal to 3. This is x1 transpose x2 equal to x1 x2 times x1 x2, and this is equal to x1 squared, x1 x2, and x1 x2 x2 squared. This is 4 value here. Okay. Is x1 x2 and x1 x2 here and x2 x1. Okay. And x2 x2 squared. Two unique values where we have x1 squared, x1 x2. Now initially at the time of figure 3 you can have three features x1. Okay. Now after the transformation, the formula of polynomial kernel, we have six features. Here we have 6 features. We have x1, x2, x1, x2, and x2 squared. Okay, so that we have 6 features. After transformation with polynomial, features can be plotted as 3D figure 4, which means that x1 will be x2, and x2 it will be x2 squared, and it will be x1, x1, x2. So the two dimensions should be x1, x2. And once we have all this point, we will find all these points. This is how we have the ability to separate and apply we have also another transformation with the radial basis function kernel. Okay, this is hyperparameters. I will show you with some examples after session. Okay, and also we have segment kernel. So this transformation of nh and sigma transpose xt plus sigma. Okay. Now I will show you this both transformation of radial basis function and the segment function. Okay. That's good for you all. So this session I want just discuss this theoretical part. Okay. After that, I will implement some examples with here and show you the parameters and how we can apply each value in its analysis. So thank you for watching. Happy learning for all. Bye bye.